Hi, welcome back. I thought I'd go over the lab on Ohm's law with you to help you get started with it. So let me first go over what Ohm's law is, and then we will go review the lab together. Okay, so I'm just going to share my screen, and I'm just going to share my little whiteboard and walk you through what Ohm's law is. So Ohm's law deals with electricity, and Ohm's law is written that V, this stands for electric potential, or voltage is another word we use for that. The voltage is equal to the current that is flowing. It stands for current, multiplied by resistance. Now, what do these three things mean? So, simplest case, if you have a battery and you connect that battery to a wire or a light bulb, okay, you're going to see the light bulb light up. And why is that happening? So I'm going to draw our little battery right here. Here's the positive end of the battery. Here's the negative end of the battery. And let's suppose we connect it with a wire to a light bulb. And then we go over here. Once we connect it up like this, we have completed the circuit and the current can begin to flow. If you don't complete the circuit and you don't connect both ends of the battery with your circuit element, like a light bulb, there's not going to be any current flowing. So the first step you have to do is make sure that your circuit is closed. What the battery does is provide what we call electric potential or voltage. And if you look at a battery, you will see that batteries have different voltage ratings. Some of them are like 1.5 volts, 3 volts, 9-volt batteries are very common. So if you hooked this up to a 9-volt battery, what does that actually mean? It means that for every amount of charge that goes through this battery, it provides a certain amount of energy. So voltage is energy per unit charge. It's kind of like another way to say, I'm adding potential energy to this system, electric potential. It's electric potential energy that the battery adds. So if it's a 9-volt battery, what that means is that it's providing 9 joules of energy for every amount of charge that passes through that battery, 1 coulomb. Remember, charge has units of coulombs. So the battery gives it a little boost, right? It's almost like a pump. It pumps, a water pump pumps water up, gives it some energy, potential energy, and then the water falls back down the fountain, right? The same thing is happening here. The battery is kind of like a pump that pumps the charge through, right? And then the charge will flow through the rest of the circuit down the waterfall. Use up all of that energy that it has, right? It provides potential energy to the charges. And then that the charge has energy as it passes through the circuit. That energy can be used to power things like light bulbs or other things. And then once it passes through the circuit, all of the energy is used up. It gets back to the battery again, and the battery again provides that boost of energy, 9 volts of energy basically, and then it continues the cycle. Okay, so that's what we mean by voltage. Right? It's just an energy per unit charge. So that's voltage. I represents current. Current is kind of It's like a water current, right? It's how much charge is flowing every second, right? So if I took a cross section right here and I could count how many charges are moving through that cross section every second, that would tell me what the current in the circuit is. Current is how much charge is flowing every second. And if I look anywhere in this particular circuit, everything is in series with each other. Like the battery is connected through the wire, is connected to the light bulb, and then it flows back through. So it would make sense that everything here is going to have the same current flowing through it. The units for current, by the way, are amps, which you've probably heard of that in your everyday life. Okay. So more amps, more amperage means a higher current. There's more charge flowing through this circuit every second. Okay. Now the last term here in Ohm's law is resistance. Just like in everyday water flowing through a river or something, there's objects in the river that create resistance to water flow. The same thing happens in a circuit. There are things within the wires and within the light bulb that create resistance to the flow of the electrons in this circuit, because that's what's flowing here, electrons. More resistance means that less, it's going to impede the flow of electrons. If you have less resistance, that's going to allow the electrons to flow more easily at a given voltage. The units for resistance are ohms. We named it after ohms. And you often see it with the symbol this. Resistance depends on the material. The material. Some materials have very low resistance, like copper, for example. Copper is a common household wiring material. It has low resistance and it allows the current to flow very easily through it. But if you look inside of a light bulb, the little filament in the light bulb actually has very high resistance. And so when the electrons get to that light bulb, it's difficult for them to flow through there. And because they're bumping into and so resistance, prevents the electrons from flowing. It depends upon the material, right? If the material has a lot of impurities in it, it just depends upon the material itself. But if it has a lot of impurities that prevent the electrons from flowing through there, the electrons are going to be bumping into these things. It's not going to be able to flow, and it's going to heat up, and it might even light up the light bulb. When you look inside your toaster, you'll see the same thing happening. You'll see the toaster filaments start to glow and heat up. That's because there's a lot of resistance in that material. The electrons are like struggling to get through there, and it's a buildup of light and heat energy. So the electrons gain energy when they pass through the battery, and then the electrons lose energy when they pass through the light bulb. And that energy is lost through light and heat if it's a light bulb. Obviously, there's a many other things you could put into a circuit that's going to use up energy, but light bulb is the simplest example. Okay. Conventional current is going to flow from the positive terminal of the battery around through the light bulb and then come back this way. So you're going to explore the relationship between electric potential or voltage, current, and resistance in the lab today. So let me bring up the lab simulation. just play around with the controls before you start to get into the lab. You can adjust voltage and you can adjust resistance. So when you adjust voltage, you notice that it makes sound. I don't know. I'll turn the sound off. But you'll notice that as you increase the voltage, that you're adding more batteries, right? As you decrease the voltage, you're decreasing the number of batteries. Okay. You can also adjust the resistance. So as you adjust the resistance, notice that in this wire, there's more black dots. The black dots represent those impurities in the metal lattice in your wire. As you increase the resistance, it's going to be harder for the electrons to flow. And you will see the current actually go down. So for a given voltage, so let's keep it at 4.5 volts, and high resistance, the current is 4.5 milliamps. Very small current. And you can see the direction of current flow by these orange arrows. Now, if I decrease the resistance, so I put in a different material that has less resistance in it, you can see the current's going up and up and up and up and up. It has to balance out because I haven't changed the voltage. The current and the resistance are always going to balance out to give me 4.5 volts. All right. Now in the lab, you're going to plot various different voltages and resistances. So you're going to complete the table. So you're going to set the resistance to be 800 ohms, and you're going to set the voltage at 0.1 volts, and then you're going to record the current that flows there, right? So let's do that. 800 ohms. Sometimes it's hard to get it right exactly on 800. 801 is close enough. And you want to start off with the lowest voltage possible, 0.1 volts. Your current is 0.1 milliamps. So you're going to record that right here. And then let's bump it up. The next one, you want to keep the same resistance, 800 ohms, and then you're going to bump up the voltage to 2 volts. Now you have 2.5 milliamps. So let's record that again. You can type it out. You can, print it out and draw your, write your answers on a sheet of paper and then send me a PDF. It doesn't matter. Next one, we're going to have 3 volts. So let's bump it up to 3 volts. We're increasing the voltage. The resistance is staying constant. So what's happening is we're basically putting in more batteries. We're providing more energy to the system by putting in more batteries. And that means there's going to be more current flow. Now it's 3.7 milliamps. Let's bump it up to 4 volts. Now we're at 5 milliamps. So let's record that here. Next one, we're going to bump it up to 5 volts. And now we're at 6.2 milliamps. Let's record that. And then the last one at this particular resistance is going to be 9 volts. All the way to the top, 11.2 milliamps. So larger voltage at a given resistance is going to be more current flow. I've provided more energy, potential energy, that's going to allow the current flow to go faster. 11.2, let's record that. Okay. And then you will do the same thing for different resistance values. So 405 ohms, you'll just drop this down. It's okay if you can't get it exactly on 405 as long as it's close enough. And then, you know, redo the whole thing again where you change the voltages and record the current. You will see more current flowing here because we have decreased the resistance down to 405 ohms. And you do the same thing for that. Drop it down again to 40 ohms and do the same process all over again. The next part is going to be graphing your data. You're going to graph the voltage on the y-axis and current on the x-axis. So what that's gonna, and so you can do that on graph paper. You can draw it out. It doesn't really matter how you do it. Let me clear all my drawings. So what this is gonna look like is you're gonna have y and x. Voltage on the y-axis and current on the x-axis. So you'll go back and look at your data that you recorded. So for a voltage of 0.1 volts, your current was 0.1 milliamps. So, hold on. If you make this, you know, maybe units of 1 volt here, 2 volts, 3 volts, 4 volts, 5, all the way up to 10 maybe. 0.1 volts is going to be pretty much down here. And on the x-axis, you know, you can have 0.1 milliamps, 0.2, 0.3. So you'll plot it right here. That'll be your first data point. The next data point we had was 2 volts and 2.5 milliamps. So it'll be 2 volts and then, you know, however you make your x-axis plotted, you can do, it would be like all the way out here basically. And that would be your second data point. And you would draw all of your data points on your graph like that. Once you have all of the data points, you will draw a line through your data points. And you want to figure out the slope of this line. Why? Well, because if I have, how do I get back to pen? Hold on. There we go. Okay. If I've plotted voltage on the y-axis and current on the x-axis, the only thing left here, according to Ohm's law, is that resistance, right? R. And that has to be equal to the slope, right? If I take voltage and I divide it by current, I'm going to get R. That's slope, rise over run, right? Y over X. So if you take the slope of this line, once you plotted your data points, you should get the resistance to be 800 ohms. Because that's what your first, set of data points was. For 800 ohms, you plotted the voltage and the current. So for this one, it should be 800. Okay. Now careful, you might have to convert because all of the currents here are in milliamps. So you're going to have to convert that into amps to get the correct value for the resistance R. So, make sure you do that when you do your plotting of the data. But that's the idea. And then you'll do it for the other resistances too, the 405 resistance and the 40 ohms resistance, and see if the slope of your line is equal to your resistance. The last question in the lab says, is it possible to decrease the resistance of the wire without changing the material it is made out of? That's a great question. Okay, so as we said before, resistance depends upon the material, right? Whether there are impurities in the material. But the resistance also depends upon a couple other things as well. It depends upon the thickness of your wire and how long your wire is. Okay. If you have a really long wire, you're actually increasing the resistance of the wire, right? Because there's just more space for the electrons to flow through. And so if you keep increasing the length of the wire, there's going to be a lot more areas for the electrons to slow down, right? To counteract that, what they do is they make the wire thicker. So that allows more space for the electrons to flow through and less resistance. So a thicker wire means less resistance. That's why when you see power lines, the power lines have to be very long, right? To counteract that, they make the power lines very thick. So if you look at the power lines, they're very thick wires. Okay. So that's what the resistance depends upon, the material itself and the impurities in the material, the length and the thickness of it. Okay, so that should help you answer the last question there. I hope this helps when you're working through this lab. If you have any other questions on it, please let me know. But until then, I'll see you.